Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So in this session, I want to discuss about solid mechanics and material subject. So this subject a very important subject in mechanical engineering. So already you know about materials and then what is the importance of materials in engineering. But in this subject, we will see the mechanics and materials. The first topic is here simple stresses and strains. So now I will explain what are the stresses are there and what are the strains, and then how to calculate these stresses we will see in this session. So before going to enter into the actual subject, you should know about course outcomes. At the end of the course, a student should be able to explain the concept of stress strain, material constitutional relationship, and strain energy induced in a linear, elastic, and homogeneous and isotropic materials subjected to forces. This is CO1. Coming to CO2, at the end of the course, the student should be able to illustrate the shear force and bending moment distribution in beams for analyzing the structural behavior under various loads. So here the course outcomes are very important in outcome based education. So after completion of this subject, the solid mechanics and materials, the student can able to explain whatever discussed in this subject. They should be able to explain the concepts of stress strain, what do you mean by stress and what do you mean by strain, what is the relation between these two, and how to calculate the stresses, and the strain energy induced in linear, elastic, homogeneous, and isotopic material subjected to forces when the component material is subjected to some force. So what are the properties induced in the material? So like that, the student can able to explain. Similarly, the CO2 also, the students can illustrate the shear force and bending moment. First, in this CO2, we will see the shear force definition, and then types of shear forces, and the bending moment definition, how to calculate the shear force and bending moment, and then how to draw the shear force diagram and the bending moment diagram also we will see in this CO2. And also analyzing the structural behavior under various loads, so we will see in the CO2. Coming to CO3, they analyze the theory of simple bending for illustrating the distribution of bending stresses across the section beams under loading. The CO4 make use of the maximum shear stress and shear stress, maximum shear stress and shear stress distribution across the depth of symmetric and unsymmetrical beams. So in this CO4, we will learn symmetrical and unsymmetrical beams whenever the loaded with various loads for the safe design of aircraft components. So make use of the maximum shear stress and shear stress distribution. At the end of the course, student be able to utilize Maxwell's reciprocal theorem, double integration method, and a moment area method for determining. The CO6 is demonstrate the principal stresses, principal planes, and torsional stresses acting on any arbitrary plane within a structure using analytical and Mohr circle methods. So we will learn the Mohr circle method, analytical method, and graphical method. We will learn first principal stresses, principal planes, and torsional stresses. After study of these, the principal stresses, we apply analytical method and Mohr circle method for calculating the principal stresses and principal strains. So these are the COs defined from 1 to 6. So now CO1, that is, the topic is simple stresses and strains. What we have to learn in CO1? Concept of stress strain. What is the basic concepts of stress strain? Material constitutional relationship. What is the relationship between this stress and strain? And also material constitutional relationship. And strain energy, linear strain energy, and elastic and homogeneous, and other properties isotropic materials. Whenever subjected to forces, we will calculate these values. So now in this session, so I will discuss, I will explain about simple stresses and strains, how to calculate, and how many types of stresses are there, we will see. First of all, introduction part. So what do you mean by stress? And what do you mean by strain? So when an external force acts on a body, the body tends to undergo some deformation. So due to cohesion between the molecules, the body resists deformation. So this resistance, which material of the body opposes the deformation, is known as strength of the material or stress. So whenever the external force acts on a body, the body tends to undergo some deformation. But this deformation, another force opposes the deformation. That is called as stress. But behind the elastic stays, the resistance offered by the material is less than the applied load. In such case, the deformation continues until failure takes place. So up to elastic stage, there is no failure and no deformation. Why? Because the resistance offered by the material is less than the applied load. So in such cases, there is no deformation, and until that failure takes place, it continues. So within elastic stage, the resisting force equals applied load. This resisting force per unit area is called as stress or intensity of stress. The resisting force per unit area, that is stress, you can represent with sigma or F is equal to load per area or force per area. Resisting force per unit area. is called stress or intensity of stress. See, here stress shown in this figure. This object is subjected to tensile force. So some load is applied on this object. The cross sectional area shown here. So how much load applied a particular cross sectional area. So whenever the load is acting on both sides in opposite direction, so that is called as tensile force. If it is in reverse same direction, this is compressive nature. So in this case, the opposed which force is resisted by the deformation. So as per definition, the opposite the deformation is known as strength of the material. So here the opposite force for unit, the opposite force that is called a strength. The stress is for unit load for unit area. So that is called as tensile stress. If it is compressive nature, the load is, so that is you will get compressive stress. So the direct or normal stress is calculated by using the following formula. The direct or normal stress. So this is direct load, direct stress, direct load, applied load, and original cross section area resisting the force. So that is called as normal stress. Why? Because here the assumption is always the object is a uniform cross section. There is no irregularity and there is a not non-uniform cross section. So in this, whatever applied load for cross sectional area, which area is resisting the force, that is called as normal stress. So the unit of stress in the SI units, the force is expressed in newtons. You can write written as N, and area is expressed as meter square. Force is in newtons and area is meters. Hence, unit of stress becomes as Newton for meter square. The area is also expressed in the millimeter square. Then unit of force becomes as Newton for mm square. Suppose it is in mm square, so you can write Newton for mm square. 1 Pascal is equal to 1 Newton per meter square. So you can write in terms of centimeter square, 10 to the power minus 4 Newton per centimeter square. 1 megapascal is equal to 1 Newton per mm square. So 1 megapascal is equal to 1 Newton per mm square. 1 megapascal, 1 Pascal is 1 Newton per mm square. So 1 megapascal is equal to 10 to the power of 6 Newton per meter square. Convert into mm. So 10 to the power 6 by 10 to the power 6 Newton per mm square. You will get 1 Newton per mm square. Clear? 1 mega Pascal is equal to 1 10 to the power of 6 Newton per meter square in mm square. So 1 Newton per mm square will get. Now, types of stresses. How many stresses are there? First one is tensile stress. The stress induced in a body when subjected to two equal and pulls as a result of which there is an increase in length known as tensile stress. So the tensile stress acts normal to the area and it pulls on the area. So normal to the area like this. So area. So the stress induced in the body where whenever subjected to two equal and equal load. So this is so for example 5 kilonewton into 5 kilonewton. So in this there is a chance of increase in length. Increase in length. So known as tensile stress. So see in this example in the figure shown tensile stress diagram. So the uniform bar is subjected to tensile load. So load here written as P. So the resisting force here shown, this is cross section. The resisting force offered opposite to this applied load. So you can calculate tensile stress is equal to resisting force. You can represent with R resisting force upon cross sectional area. The resisting force nothing but tensile load upon cross sectional area is A. So now the stress you can calculate load per area. So this formula already I told you in the previous slide. So the ratio of next one is tensile strain. So tensile stress already you studied. So what are the units? Newton per meter square or Newton per mm square. Newton per mm square. So now tensile stress, tensile strain. Tensile stress already we have learned. So what do you mean by tensile strain? The ratio of increase in length to the original length is known as tensile strain. So in tensile stress, what will happen whenever the tensile load applied, some deformation will be there. Due to the deformation, what will happen? The length will be increased. So now calculate how much increased. See in this dotted line, in this diagram represented as dotted lines, the increased length and decreased diameter. So the ratio of increase in length to the original length known as tensile strain. Breadthways B and B dash. B dash is the new one, B is the previous one. The extension, how much extension occur? DL, that is you can represent with delta L also. Deformation. So how much increased length? Delta L by L. The original length, the change in length, increase in length by original length. So you can calculate like this. The tensile strain is given by increase in length by original length. That is dl by L or delta L by L. This is called as strain. Epsilon you can represent it with the symbol epsilon. Next, compressive stress. The stress induced in a body when subjected to two equal and opposite pushes. So in the compressive stress, two equal and opposite. In tensile stress, same direction, but in tensile stress also equal loads, but in opposite direction, opposite pushes, because of which there is a decrease in length of the body, is known as compressive stress. The compressive stress acts normal to the area and it pushes on the area. So cross section shown in this diagram, and the resistance force the same as tensile stress, but the only thing is a type of load is compressive load. So in this, length will be decreased and diameter wise the diameter will be increased. So how do you calculate the compressive stress? The compressive stress is resisting force upon area, the load per area, that is push area. In this tensile case, full area. In this full pushing. So load per area. Here also units Newton per meter square or Newton per mm square. Next, compressive strain. The ratio of decrease in length to the original length is known as the compressive strain. So length will be decreased in this shortening. So much decreased to the original length. But the diameter width wise, the breadth will be increased. So dl is how much decreased? dl or delta L. So the dotted line represents after applied load, compressive load, the length, the shortening area. Now the compressive stress strain is equal to decrease in length upon original length, dl by L or delta L by L. Change in length upon the original length. Next one is third type is shear stress. The stress induced in a body when subjected to two equal and opposite forces which are acting tangentially across the resisting section, because of which the body tends to shear off across the section, is known as shear stress. The stress induced in a body when it is subjected to two equal and opposite forces. So which are acting tangentially across the resisting section. Then the body tends to shear off across the section. See, in this diagram shown, this is a riveted joint. So whenever this riveted joint subjected to the shear force, there the type of load is shear load. then what will happen? The shear stress is the stress which acts tangential to the area. It is represented by T. The body tends to shear off across the section. Here, see, here shear off you can see in this figure. So now the shear stress, how do you calculate? Represented with tau, shear resistance by shear area. So that is R upon area. Shear stress, shear load, and resistance force and resistance after shear off. So it is measure the shear strain. It is measure of the angle through which a body is deformed by the applied force, denoted by psi. The shear strain is represented by the angle through which the other two faces have rotated. So as the bottom face of the block is fixed, the face ABCD will be distorted to ABC1 D1 through, I will show you the diagram, an angle psi as a result of P. So ABCD and ABC1 D1. A, B, C, D and then A, B, C1 D1. So at the bottom face of the block is fixed. This one is fixed. But the face ABCD will be distorted to ABC1 through an angle psi. So much angle made with a new surface. So that is result of force. So it is denoted by psi. The shear strain is represented. So how much deformed? How much deformed in terms of psi? That is angular deformation. T2 D1 DL and the length C2 C1 and a height h. So now calculate shear strain. So the transversal displacement upon distance CD. The transversal displacement is DD1 upon distance CD, DL by H. The transversal displacement. DD1, that is DL upon AD. The distance AD is H. So DL by H. Transversal displacement upon distance AD. Next, linear strain. The linear strain you can represent with epsilon 1. When a body, the epsilon L, when a body is subjected to an axial tensile load, there is an increase in the length of the body. Already we know. But at the same time, there is decrease in other dimension of the body at right angles to the action of the applied load. Thus, the body is having axial deformation and also deformation at right angles to the line of action of the applied load. So that is called as lateral deformation. The ratio of axial deformation to the original length of the body is known as longitudinal or linear strain. Original length of the body to the axial deformation to the original length. That is called as longitudinal strain or linear strain. You can represent it with epsilon L. See in this diagram shown, the original diagram having L length. After deformation, after applied load, so the length will be increased. So much increase here. This is delta L and DL. Suppose the length, total length is now L plus delta L. So the original length of the body is L, and then delta L is increase in the length of the body in the direction of P. So the P is tensile force acting on the body. And L is equal to length of the body. So diameter wise, see, the original diameter is D. After deformation, what will happen? Length is increased and the diameter is decreased. So how much decrease here? D minus delta D. And width also, B minus delta B. Next, lateral strain. Tangential strain or lateral strain. Epsilon T. So here delta L is increase in length, delta B is decrease in breadth, and delta D is decrease in depth. The linear strain is equal to decrease in breadth upon original breadth. So how much decreased? So that is change in breadth. So here we are taking lateral dimension, the breadth or diameter. In previous case, linear strain, we are taking length, linear dimension. That is the difference between these lateral strain and linear strain. Next, Poisson's ratio. That is mu r 1 by m. Now, it is defined as the ratio of the change in the width per unit width of the material to the change in its length per unit length because of strain. Also, it is defined as the ratio of lateral strain to the linear strain. So, mu, the Poisson ratio you can write mu r 1 by m is equal to the ratio of lateral strain to linear strain. Lateral strain to linear strain. So this is called as Poisson's ratio. For most common materials, the Poisson ratio is in the ratio of 0 to 0.5. So here seen the ratio range also 0 to 0.5. So the Poisson's ratio values for different materials shown in this diagram. So material and values. For concrete, the Poisson ratio shown 0.1 to 0.2. Cast iron 0.21 to 0.26. Steel 0.27 to 0.30. So sometimes we have to remember these values. So why? Because in our strength of materials problems, while solving the problems, so you should assume some values. Poisson's ratio, that is depending upon the material. Sometimes they may give or not. So that's why remember the approximate value. The rubber 0.499. So you can take 0.5. So the gold is 0.4 to 0.44. So all these values range between 0 to 0.5 only. The maximum value is 0.5, where it is foam 0.5. Similarly, glass 0.182, 0.3, cork 0, and copper 0.33, and clay 0.302, 0.45. The stainless steel 0.302, 0.31, and foam 0.12, 0.5. Next, Hooke's law, very important law in this simple stress and strains. It states that the strain in a solid is proportional to the applied stress within the elastic limit of that solid. The strain in a solid proportional to the applied stress within the elastic limit of that solid. So that is sigma, or sigma stress directly proportional to the strain. Strain has no units as it is a ratio. This is only ratio. So that means delta d by d or delta L by L. Thus E has the same units as stress. What is this E? Young's modulus. This it is a so relation whenever the stress is directly proportional to the strain, you can write in terms of E. Similarly, for elastic materials, the shear strain is found to be proportional to the applied shear stress within the elastic limit. Tau is equal to G gamma. G is here shear modulus. E is Young's modulus. So here, so sigma directly proportional to strain, you can write like this: sigma is equal to E into strain. E is Young's modulus. Tensile stress upon tensile strain. Compressive stress or compressive strain. So Young's modulus E is equal to sigma upon E. So Young's modulus for some material shown here: mild steel Young's modulus 200, aluminum 70, copper 100, cast iron 90, bronze 120, and wood is 10. How to assume these values while solving the problems? So sometimes they will give the direct values, so this mild steel or aluminum values for further calculations. If not given, you should remember and you should assume mild steel value and then aluminum, copper, or cast iron, or bronze, or wood. So extension or shortening of a bar. So consider a prismatic bar of length L and a cross-sectional area is subjected to axial force P. Have the relation sigma is equal to E epsilon. Upon substitution of epsilon and sigma in that equation, we get PL by E is equal to P by A stress upon delta L by L strain. Now we can write into delta L. So further, you can write like this: delta L by can also be written as delta L is equal to PL by A. E is equal to PL by A into delta L. Next, delta L is equal to PL by A. The factor of safety. It is defined as the ratio of ultimate tensile stress to the working or permissible stress. It may be written as factor of safety ultimate stress by working stress for brittle materials. In the case of brittle materials, yield strength. So, what is the maximum strength upon the working? The working stress or design stress. Design stress or permissible stress. So, all these are same, the working. So, how much the actual stress also you can say, you can write like this: actual stress is called factor of safety. So, while designing any component, first you should calculate the factor of safety. So, what is the importance of factor of safety? To avoid failures, you should take this factor of safety value. See, uh, here one simple problem we will see. A rod 150 centimeter long and diameter is 2.0 centimeter is subjected to an axial full of 20 kilonewtons. If the modulus of velocity of the material of the rod is 2 into 10 to the power 5 Newton per mm square. So the modulus of velocity or Young's modulus, both are same. So what he has asked, determine the stress. So already we have studied about stress and types of stress and how to calculate. And strain also we have learned. The elongation also we already we have seen. Now calculate the stress, apply first stress formula and calculate, substitute the given values and then calculate. Similarly strain and elongation. First of all, given data is important for any problem what he has given. So given is here length 150 centimeter or convert into meters or mm. Diameter is 2 centimeter. 2 centimeter. And load is P is 20 kilonewtons. So the modulus of velocity E that is given 2 into 10 to the power of 5 Newton per m. So now determine the stress. Stress sigma load per area. So strain change in length by original length. Elongation. So how much increase or decrease the rod after applying this 20 kilonewtons. So now the given length of the rod 150 centimeter, D 2 centimeter convert into 20 mm. Similarly, this 150 centimeters also convert into mm. So the area, first of all, calculate the area. The area, how do you calculate? That is based on the given cross section. Here, the rod, the given section is rod. So the rod is circular rod. So what is the area? 5 by 4 into d square. So 5 by 4 into d square, the diameter is given 20 and calculate, you will get 105 newtons. The length, the load 20 kilonewtons. Modulus of velocity given. Now calculate stress. So stress formula load per area. How much load given? 20,000. So upon area already calculated 100 by. So calculate, you will get 63.662 newtons per mm square. Units are important. Next, using this equation, already we have studied in the previous. The strain is defined as E is equal to Young's modulus is equal to stress upon strain. Why? Because as per according to the Hooke's law, the stress is directly proportional to strain. Clear? So now you can write stress is equal to with the help of Young's modulus or modulus elasticity. So now E is equal to, you can write like this. Now strain calculate. Sigma already you calculated. E also given. Now the strain is 0.00318. This strain is a unitless parameter. So now third one is elongation is obtained by using equation that elongation E is equal to dl delta L by L or dl by L or delta L by L. So otherwise sigma is equal to PL by AE. So delta L is equal to PL by AE. So now calculate delta L elongation or otherwise apply this formula strain dl by L. So substitute the above values, you will get value 0.0477 centimeter. Clear? So like this, you have to calculate stress and strain and elongation. So these are the references I have taken. Ramamurtho, the strength of materials, the title is strength of materials. The name of the publication is Dhanpeth Rai publication. And R.K. Rajput, strength of materials, Echan publication. And Bansal, strength of materials book, Lakshmi publication. R.S. Kurmi, strength of materials. This one also Echan publications. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.